Morning, everyone. Morning. I'm good. Yourself? Questions while we wait for people to come in? Today we're going to discuss L'Hopital's rule. Questions about earlier topics, though? How is the material going? Morning, Michael. Morning, everyone. Come on in. Questions while we wait? No? Nobody? We're good? Well, let me ask you this then, while we're waiting. We saw that these three forms, 0 over 0, infinity over infinity, and infinity minus infinity, we saw that these were indeterminate forms. Morning, Benjamin. Morning, everyone. Come on in. Right, we saw that these were indeterminate forms. Do you have readily available examples to convince yourselves that just by knowing the limit has one of these forms, we are not able to evaluate the limit just by knowing that? Meaning that anything can happen. Do you have these examples available to you now without looking? Anybody? Can anybody give me an example of a limit that has the form 0 over 0, but where the limit can be anything? you need to have these x squared minus 1 over x minus 1. I'm going to assume the limit as x goes to 1. Very well. So Seelan has given me this, which does have the form 0 over 0, but obviously the limit, I mean, I shouldn't say obviously, but the limit is 2, right? So that's an example where the limit is 2. What about limit being anything else? I think Benjamin was also suggesting the limit as x goes to 0 of x over x. So this limit is easily seen to be 2. This limit is easily seen to be 1, right? So right? So here the limit is 1, here the limit is 2. These both have the form 0 over 0. Right? And if we look at this one and or this one and you multiply by any number you want, this still has the form 0 over 0, but in this case the limit is 14. And so on and so on, right? If you multiply this by 6, this still has the form 0 over 0, but the limit is 6. And so on, right? So that's why this limit 0 over 0 is indeterminate, because anything can happen. Similarly for infinity over infinity, right? In fact, this same example works out. Limit as x goes to infinity of x over x. This limit is easily seen to be 1. And if you multiply it, well, right, I mean, it does have the form infinity over infinity. If you multiply this by 6, let's say 16, it's still infinity over infinity, but the limit is easily seen to be 16, and so on and so on. What about infinity minus infinity? Anybody have an example of a limit that has the form infinity minus infinity? But where the limit would be 1, say? X squared minus x. What is that limit? What is the limit as x goes to infinity of x squared minus x? This certainly has the form infinity minus infinity. Let us factor out an x. And if we factor out an x, we see that this goes to infinity. This goes to infinity. Infinity minus 1 is infinity. And we have infinity times infinity, which is infinity. So this limit is actually infinity. Can we come up with an example where infinity minus infinity would be 1? X minus x, or right, this is infinity minus infinity, but of course this limit is easily seen to be 0. Morgan is asking why it isn't minus 1. Its limit as x goes to infinity, right, not 0. And Shamir is pointing out if you had x minus x squared, then of course with the same work, this limit would be negative infinity. And can we manipulate this to get a limit of 1 instead of 0? Can we fix it to make it 1 instead of 0? Anybody? You should have these examples. We saw them in class. You should have them readily available to you. As x goes to infinity, 1 over x goes to 0. 2x minus x is just x, so that goes to infinity. Two x minus x over x, well, that's going to be infinity over infinity. So you get infinity minus infinity over infinity. Not exactly what I wanted. Thank you, Shamir. X plus 1 minus x. Right? As x goes to infinity, this goes to infinity, this goes to infinity, so you have infinity minus infinity, but of course the x's cancel, and you're just left with 1. And you can change that to a 4, and the limit becomes 4, and so on and so on. Right? You need to have these examples immediately available to you to convince yourselves that these are indeterminate forms, and to convince your friends taking this course, or your friends that are going to take this course next year, when they ask you, why is this an indeterminate form, you're going to present them with examples where the limit tends to anything you want it to. All right. Why am I talking about these indeterminate forms? Well, a lot of you are familiar with L'Hopital's rule, which is what we're going to discuss today. 0 times infinity is indeterminate as well, absolutely, right? So we have other indeterminate forms. 0 times infinity. 0 times infinity. Do we want to discuss that quickly? Somebody give me an example where you have a limit that has the form 0 times infinity, but whose limit is 1. X times 1 over x, thank you. If you want, just take limit as x goes to 0. So this goes to 0, this goes to positive infinity, so you have 0 times infinity, but of course you see the limit to be 1. Celine, I'm not understanding what you mean here. In our examples, we multiplied 0 times infinity. Right, I'm suggesting, or in fact you were suggesting, when you solve the limit as x goes to infinity of x minus x. Well, x minus x was just 0, right? So we're not multiplying. Right, but so you're suggesting you're going to factor out an x and you get 1 minus 1. But 1 minus 1 is the number 0. It's not something that tends to 0. When I say 0 times infinity here, I mean in the context of limits where you have one limit tending towards 0, whereas the other limit tends towards infinity. Right? Take this example. As x goes to 0, this approaches 0. It never reaches 0, right? It approaches 0. And this approaches infinity. So when I say 0 times infinity, I mean things that approach 0 times things that approach infinity. Because if you have the actual number 0, you know that 0 times anything, 0 times any other number, is going to be 0. So if it's the actual number 0 times another number, then the answer is going to be 0. So let's consider L'Hopital's rule, a very important theorem, very useful, but you want to be careful. So first, let me start by stating it. Let f of x and g of x be differentiable and g prime of x not equal to 0 on an open interval containing A except possibly at A itself. Suppose that limit as x goes to A of f is equal to 0, and so is the limit of g. Or some sort of infinity. Then the limit as x goes to A of f of x over g of x, right? So if both limits go to 0, then this has the form 0 over 0, or some sort of infinity over possibly some other sort of infinity. It doesn't matter whether it's positive or negative, right? So this has the form 0 over 0 or infinity over infinity. Then this is equal to the limit of f prime over g prime, if this limit exists. Right, so L'Hopital's rule, a very powerful tool to help you evaluate limits of the form 0 over 0 or infinity over infinity. Right? Now you see why everybody wants to use it, because you can just differentiate the top and differentiate the bottom. Keep in mind, you're not applying a quotient rule here, right? Don't get those two things confused. This is L'Hopital's rule. L'Hopital's rule tells you if you have a limit that looks like 0 over 0 or infinity over infinity, you can differentiate the top and differentiate the bottom. What are L'Hopital's rule limitations? Well, I mean, of course, it has to your functions have to satisfy the hypotheses, of course. We usually do some hand waving there. But the real answer is sometimes, well, as you'll see, we'll see an example of the limitations of L'Hopital's rule. And Jennifer is asking, why does that work? So you're really asking for the proof of L'Hopital's rule. Let's convince ourselves via a few examples, and we'll come back to the proof. Consider this. So, we're looking at limits. You know what to do. When you've got a limit, the first thing you want to do is plug in. Plug in and see what happens. If you get an answer, you're done. And when x is -2, -2 cubed is -8, plus 8 is 0 over 0. You have a 0 over 0. So you can apply L'Hopital's rule, right? You're in a L'Hopital's rule situation. You can apply L'Hopital's rule if you wanted to. You don't have to, right? In this case, you know what could be done here, right? But let's apply L'Hopital's rule, see what happens. The derivative of the top, 3x squared. The derivative of the bottom is 1. Answer is 12. Very easy. Thank you, Matthew. How would we have done this otherwise? If we had not used L'Hopital's rule? -2 is a root. So you know that x minus -2 or x plus 2 must be a factor. And you could have factored this as x plus 2 times some stuff, using long division or otherwise. Can we just cheat here? I need an x squared. So x times x squared is the x cubed that I want. And then I get a 2x squared. I don't have that, so let me subtract the 2x squared. But then I get a -4x, and I don't have that. So let me add a 4x, and then I get the +8. Perfect. And then these cancel, and as x goes to -2, this is 4 minus -4, so 8, 9, 10, 11, 12. Exactly the same answer. Thank you, Matt. Right, long division gives you the x squared minus 2x plus 4. Consider this. Again, we're taking a limit. First thing you want to do is plug in. What are we working with? As x goes to 0, tangent of 0 is 0, sine of 0 is 0. So we have a 0 over 0. It's important that you make sure that you're in a L'Hopital's rule situation before you apply L'Hopital's rule. Because if you don't have a 0 over 0 or infinity over infinity, you cannot apply L'Hopital's rule. But we do have it here. So we can differentiate. Differentiate the top. Derivative of tangent is secant squared times the derivative of the inside. Chain rule, right? Derivative of the bottom, cosine 2x times the derivative of the inside. Thank you, Michael. And as x goes to 0, secant of 0 is 1. Cosine of 0 is 1. So we get a 3 over 2. Right? Somebody's asking, it can only be 0 over 0 or infinity over infinity, not any other indeterminate form in order to use L'Hopital's rule. That's exactly correct. Only infinity over infinity or 0 over 0. Nothing else. So we get a 3 over 2. Of course, you knew how to deal with that regardless, right? You didn't need L'Hopital's rule here. You could have rewritten this in the form tangent is sine over cosine. And you could have taken this a step further. You're dividing this fraction by sine x. You know the sine x goes into the denominator. This is sine of 3x over cos of 3x times sine of 2x. And then you would have Kamal was asking, what would another indeterminate form other than 0 over 0 or infinity over infinity? You know that infinity minus infinity is another indeterminate form. 0 times infinity is yet a fourth, and we'll see 3 others momentarily. Right, and here, if you multiply by 3x times 2 over 3x times 2, you multiply by 1, you're not changing anything, and you're going to, well, I don't have to tell you what you're going to do. You know exactly what you're going to do, right? Because you had a question like this on the midterm. So you can group this together, and you can group that together, and leave everything else outside. So 3 over 2, sine 3x over 3x, 2x over sine 2x, and finally 1 over cos 3x. This, you can take an extra step if you wish and rewrite it as 1 over sine 2x over 2x. So that as x goes to 0, this whole thing goes to 1. This goes to 1, right? Because you know sine of theta over theta goes to 1 as theta goes to 0. As long as the argument goes to 0 at the same rate as the denominator, the limit is 1. So this goes to 1, this goes to 1. As x goes to 0, cosine of 0 is 1. So this goes to 1 as well, leaving you with 3 over 2. Exactly the answer you got in one step with L'Hopital's rule. So you see the power of L'Hopital's rule, right? Instead of doing 5 or 6 steps, 1, and you're done. That's why people like it. Will there be a midterm question that requires L'Hopital's rule? Final, very good. Possibly. For sure, L'Hopital's rule is now fair game. Consider this. As x goes to infinity, what is happening? As x goes to infinity, this goes to infinity. Square root of infinity is infinity. And ln of infinity, well, you know the graph of ln. But as x gets larger and larger, ln goes off to infinity. So if the numerator goes to infinity, denominator clearly goes to infinity. So we have an infinity over infinity. And if you didn't have L'Hopital's rule, this would be a very, very difficult question to answer. Luckily, we do have L'Hopital's rule. Since it's the square root here, let's take a moment to simplify that ever so slightly. Right, this is x to the 1/2, and you know you can pull down the 1/2. And this still has the form infinity over infinity. Why does the numerator go to infinity? Well, the square root of x goes to infinity. And you know the graph of ln x. As x goes to infinity, ln goes to infinity as well. Exactly as Michael pointed out. So this has the form infinity over infinity. So here we can apply L'Hopital's rule. And we get 1/2 times 1 over x. Derivative of ln x is 1 over x. Derivative of the denominator is 2x. And we can rewrite that as 1 over 4x squared. As x goes to infinity, this goes to 0 and we're done. Consider this. What is hyperbolic sine of 0? Well, we're not sure. But you know what hyperbolic sine is. Right? It's e to the x minus e to the minus x over 2. So when x is 0, you get e to the 0, which is 1, minus e to the 0, which is 1, over 2. In other words, it's 0. So as x goes to 0, this goes to 0, and this goes to 0. So the numerator goes to 0, denominator goes to 0 as well. We have a 0 over 0. we can use L'Hopital's rule. Derivative of hyperbolic sine. Benjamin, you know there's no h here. It's not sine of hx, it's hyperbolic sine. Exactly that. Derivative of hyperbolic sine. You know what it is. It's hyperbolic cos, thank you. Derivative of the denominator, 3x squared. Well, now the obvious question is, what is hyperbolic sine, hyperbolic cosine of 0? And you know that hyperbolic cos is e to the x plus e to the minus x over 2. So hyperbolic cos of 0 is 1 plus 1 over 2, which is 1. Right? So as x goes to 0, this goes to 1. 1 minus 1 is 0 over 0. And as Michael suggests, you're still in a L'Hopital's rule setting. You can apply L'Hopital's rule once again. Derivative of the top. Derivative of hyperbolic cos is hyperbolic sine again. Derivative of 1 is 0. Derivative of the denominator, 6x. And as x goes to 0, hyperbolic sine of 0 is 0. Denominator is 0. You still have a 0 over 0. You can apply L'Hopital's rule again. Derivative of hyperbolic sine is hyperbolic cos. Derivative of the bottom is 6. Seemingly endless, right? But, you know, you were seeing what was happening to the denominator. You know that it's not going to be endless because eventually the denominator is not 0 anymore. And we're at that stage right now. The denominator is not 0, so you're not going to get a 0 over 0. So you're not going to be able to apply L'Hopital's rule in this next step. Denominator is not 0. Numerator, cosine of 0 is 1. 1 over 6 is the answer. How are we doing? What if it keeps going? Exactly. Exactly. I don't have an example, so let me make one up. Wouldn't the answer be negative 1 over 6? I think your mistake, Benjamin, might lie in the fact that the derivative of hyperbolic cos is not negative hyperbolic sine, but rather positive hyperbolic sine. Right? The hyperbolic trig functions don't work exactly the same as the trig. Right, so Morgan is asking the good question here, what if it keeps going? And let's consider this example. As x goes to infinity, This goes to infinity. Infinity plus 6 is infinity. Square root of infinity is infinity. So you have an infinity over infinity. You can decide to apply L'Hopital's rule. Nothing wrong with that. You're in the correct setting. And if you do, derivative of the top, 1 over 2 square root times the derivative of the inside, all over 1. Clean that up a bit. If we clean that up a bit, what do we get? The 2's cancel out nicely, and we have x over the square root of x squared plus 6. As x goes to infinity, the denominator still goes to infinity, and so does the numerator. This is still infinity over infinity. So, we're allowed to use L'Hopital's rule. Differentiate the top. Differentiate the bottom. Derivative, the bottom is the square root. So 1 over 2 square root times the derivative of the inside times the 2x. Might as well cancel the 2's while I'm here. And now you've got 1 divided by a fraction. So we're going to multiply by the reciprocal. And this is square root of x squared plus 6 divided by x. Exactly what you started out with. So you see the issue. You still have an infinity over infinity. You can apply L'Hopital's rule once more, twice more, and you're back. So you get this ever circular argument, and it never ends. Well, that's exactly what you want to do, Michael. Michael is suggesting to factor out an x squared from the square root. And now you know that the square root of a product is the product of the square roots. So you get absolute value of x, 1 plus 6 over x squared. And since you're dealing with positive numbers, you don't need the absolute value. It's just x. The x's cancel. As x goes to infinity, this goes to 0. The whole thing goes to 1. What's the point? The point is that while L'Hopital's rule is a very powerful tool, it doesn't answer every single question. And even if you are in a L'Hopital's rule setting, it might not work anyway. So that's why we had to learn all of these techniques beforehand. They're still very important. This simple limit, L'Hopital's rule fails us in trying to evaluate that. Of course, as Matthew suggests, you can use a combination of L'Hopital's rule and other techniques. As long as you're not doing anything illegal, it's fine. So maybe apply L'Hopital's rule first and then do something else. It's all good. Absolutely. Consider this as x goes to infinity. What are we looking at? So x goes to infinity, this goes to infinity. This goes to infinity. With the negative, makes it a negative infinity. E to the negative infinity is e to the negative infinity, which is 1 over e to the infinity. 0, thank you. So this has the form infinity times 0. Wait, I'm getting 3 different answers here. You know the graph of E. As x goes to negative infinity, e to the x, or e to the negative infinity, goes to 0. So we have infinity times 0 here, an indeterminate form. An indeterminate form, but we're not in a position to use L'Hopital's rule right away, right? Because L'Hopital's rule is for infinity over infinity, or 0 over 0. But as Michael suggested, because of the negative exponent here, we could rewrite this in this way. And now we have an infinity over infinity. Now we're in a position to use L'Hopital's rule. Differentiate the top. Differentiate the bottom. Chain rule, right? The 1/2s cancel. Let's clean that up by rewriting this as 1 over root x, e to the x over 2. And as x goes to infinity, this goes to infinity. This goes to infinity. E to the infinity is infinity. So you get a 1 over infinity, which is 0. So Matthew, in theory, yeah, you could have a question and where you would have to use L'Hopital's rule a few times, maybe, and then other techniques. Absolutely. How many more web works? I think 1 or 2. Very few. Why did the root x come down? Zoe, you tell me. What did we do from here to there? Would we deal with negative infinities in the same way, right? L'Hopital's rule isn't specific to positive infinity versus negative. Any kind of infinity is fine. Because as you know, with limits, you can always pull out constants. So negative infinity could be viewed as -1 times infinity. You could pull that out. Back to Zoe's question here. We applied L'Hopital's rule, right? So we differentiated the top, differentiated the bottom. The derivative of root x is exactly that. The 1/2 did cancel. This 1/2 and that 1/2. Oh, so you mean from this step to that step. So what do we have there? We have A over B all over C, right? A over B all over C. So this is A over B divided by C. And when you divide by something, it's the same as multiplying by the reciprocal. So A over BC. In other words, this moves back up there. I'm just saying a fraction in general. If you have a fraction divided by something, no, but I mean, this is 1/2 times 1 over root x. Right, so I'm canceling the 1/2s. I still have a 1 over root x. It's all good. Seelan, it's a good question. Seelan is asking, when you have infinity times 0, which function do you bring on the bottom? Is there a general trend for which one you bring on the bottom? What can I say about that? Well, I mean, I'm sure you could come up with some rules. Let's not look for rules. Instead, let's be smart and say that you're hoping that by applying L'Hopital's rule, the expression becomes simpler. Simpler to deal with, simpler to work with. And that's what's important. And that basically determines which function should go on top, which function should go on the bottom. Let's take this example right here. As x goes to negative infinity, 1 over x goes to 0. Log of 1 is 0 times negative infinity. So you have an infinity times 0 here. So we're going to mimic what happened here. We're going to bring a function into the denominator. But now you're thinking, well, I mean, none of them have a negative exponent. So that's an issue. But observe that x is the same thing as 1 over x. Right? Because this is 1 divided by 1 over x. And when you divide by a fraction, you multiply by the reciprocal. So a very nice, useful trick, which allows us to rewrite this in one of two ways, right? Either as ln of 1 minus 1 over x over 1 over x, or the opposite, right? You could have left the x on top and have written this as x over 1 over the ln. Either way, would have been correct. However, observe what happens if you do it this way instead of the other one, right? Here the point is, as x goes to infinity, this goes to 0, ln of 1 is 0, and as x goes to negative infinity, this goes to 0. So you have a 0 over 0 here. You're in a L'Hopital's rule setting. We can differentiate the top, differentiate the bottom. The derivative of ln is 1 over 1 minus 1 over x times the derivative of the inside, chain rule, right? Which is 1 over x squared. And the derivative of the bottom is negative 1 over x squared. So Matthew is asking if L'Hopital's rule can only be applied to fractions. Well, you need a 0 over 0 or infinity over infinity. Absolutely. The x squares cancel out nicely. As x goes to negative infinity, this goes to 0. So this goes to 1. You've got a negative there. So negative 1 is the answer. I've got a 1 over x squared both on top and on the bottom. I'm canceling these, but I've got an extra negative there. It is 0 over 0, but I mean, it's something over itself, so you can cancel. Matthew, absolutely right. For other forms, if you're really intent on using L'Hopital's rule, you have to convert them into 0 over 0 or infinity over infinity. Consider this. As x goes to infinity, this goes to infinity. 1 over x goes to 0, sine of 0 is 0. So this has the form infinity times 0. Perhaps before we attempt this, let me go back to this one. And you know, I was saying you had the option of rewriting this as x over 1 over ln. Right, that's still true by this argument here. Ln is 1 over ln. But by writing it this way and applying L'Hopital's rule, observe that one application of L'Hopital's rule, the ln is gone. However, here, if you apply L'Hopital's rule, the x will disappear, but you have to differentiate this business, which is going to be a complicated expression. Oftentimes suggesting that this might not be the way to go. Not always, but yeah. So that's really kind of what you're looking for when you're trying to decide, you know, if you've decided that you're going to use this idea, x is 1 over x, in order to transform it into 0 over 0 or infinity over infinity. You want to look forward and ask which is better to leave on top. And in this case, the lawn is better. Let's look at this. Right, this has the form infinity times 0. So you're not able to apply L'Hopital's rule immediately. What are we going to do? We're going to manipulate, as we usually do. And we can rewrite this as the same trick. X to the 3 over 2 is 1 over x to the 3 over 2. And now as x goes to infinity, 1 over infinity is 0, sine of 0 is 0, 1 over infinity is 0. We have a 0 over 0. We can apply L'Hopital's rule. The derivative of the top, derivative of sine is cos, times the derivative of the inside. The derivative of this, negative 3 over 2, x to the negative 5 over 2. We can cancel the negatives. Negative exponent in the denominator is going to be the same as a positive exponent on top. So this is really the same as 2 over 3. This is going to be an x to the 5 over 2. And it's going to cancel with this x squared, leaving me with an x to the 1/2. Does everybody see that? Why are they negative? Well, it's just the chain rule, right? Derivative of sine is cos. And then you differentiate the inside. This is x to the negative 1. The derivative is negative 1x to the negative 2. And this is x to the negative 3 over 2, whose derivative is negative 3 over 2x to the negative 5 over 2. Kamal was asking for the last question, why wasn't the numerator negative as well? Well, we have this negative here. The derivative of this is negative 1 over x squared, but you've got this extra negative there. Took out the 2/3 right here. Well, it's 1 over 3 over 2. So 1 over 3 over 2, 1 divided by 3 over 2. When you divide by a fraction, you multiply by the reciprocal. So now, right, perhaps we should finish this. As x goes to infinity, whenever x goes to 0, cosine of 0 is 1 times infinity. The whole thing is infinity. Convinced? How are we doing here? Questions? Let's consider this one. x minus ln x as x goes to infinity. What are we looking at? As x goes to infinity, this goes to infinity. Ln of infinity is infinity. So this has the form infinity minus infinity. You know this to be an indeterminate form. Anything can happen. What are we going to do? I suggest factoring out an x. Factor out an x, see what happens. What are we left with? One minus ln x over x. My question to you is, what is happening to this? What is the limit as x goes to infinity of ln x over x? Well, who knows? Nobody knows. But what we do know is that it has the form infinity over infinity. Exactly. So we can apply L'Hopital's rule to this. And what happens here? Derivative of ln is over. Derivative of x is 1. Limit as x goes to infinity. You see what's happening? What is the limit? Everyone? Limit is 0. Absolutely. So, as x goes to infinity, this business goes to 0. So the stuff in the brackets goes to 1. This goes to infinity. So you get infinity times 1, which is infinity. Exactly that. Well, as you know, Matthew, a limit of a product is the product of the limits if both limits exist. So this limit exists and it's equal to 1. This limit exists and it's equal to infinity. So the answer is infinity times 1, which is infinity. How could we proceed without L'Hopital's rule? Right? With great difficulty is the answer. With great, great, great difficulty. Let us consider 3 other indeterminate forms. What have we seen so far? 0 over 0, infinity over infinity, infinity minus infinity, infinity times 0. Let me suggest 3 others. 1 to the infinity, 0 to the 0, infinity to the 0. Why? Why is 1 to the infinity an indeterminate form? As you know, this is in the context of limits, right? So it's not the actual number 1, but rather something that is getting closer and closer to 1. So if you had something bigger than 1, and you're taking large powers of that, then that's going to go off to infinity. 1 to any power is 1. If you took something less than 1 and you took large powers, that would go down to 0. So is the answer 0? Is it 1? Is it infinity? Who knows? Anything can happen. Maxwell was asking for the other indeterminate forms. We have these 4 forms originally, and now these 3 others. So I think I have convinced you that 1 to the infinity, anything can happen. Or at least 3 different answers immediately without doing too much work. What about 0 to 0? Well, you're thinking to yourself, anything to the 0 is 1, but 0 to any power is 0. So is the answer 0? Is it 1? We want to go through this again. You're thinking to yourself, 1 to any power is 1, but this is in the context of limits. So it's not necessarily the number 1, but something approaching 1. What if it was bigger than 1? What if it was something larger than 1, tending to 1? If you take something bigger than 1 and you take very large powers, it's going to be a very large number. If you took something less than 1 and you took very large powers of that, then it would go down to 0. So is the answer 0? Is it 1? Is it infinity? Who knows? And finally, infinity to the 0. Again, you're thinking to yourself, anything to the 0 is 1. But any power of infinity is going to be infinity. So is it infinity? Is it 1? We'll see that it can be anything. And Matthew's asking, isn't 1 to the power anything equal to 1? But you have to understand that this is in the context of limits. It's not the actual number 1. Why don't we start with an example of exactly that? The point is that these 3 forms are treated in exactly the same way. And I'll show you how we treat them via this example. Consider this. As x goes to infinity, this goes to 0. So this has the form 1 to the infinity. And you see what's happening, right? If you take a very, very large number, like 1,000,000, this is 1 plus 1 over 1,000,000. So it's a number bigger than 1. And then you're taking that to the power 1,000,000. So again, I claim that this is an indeterminate form, and we'll see what happens, right? I mean, some people know the answer already. We'll see that this is E, and how are we going to see that? Well, 1 to the infinity is hard to work with here, right? This power is hard to work with. We're going to change the question. We're going to change the question by taking the log of the whole thing. I'm changing the question. These are not equal. So I haven't put them as equal, right? You see that there's no equal sign there. I'm changing the question by taking the log. What does that do? That allows me to bring the power down. And that's why all these 3 cases are treated in the same way, because they all have powers, and by taking a log, that allows you to bring the power down. has x, well, I mean, we are changing the question. So let's not worry about that for now. But we will have to adjust our answer in the end. Right? The answer we get here will not be the answer to this question. But taking a ln allows us to bring the power down, making everything simpler. What happens? As x goes to infinity, 1 over x goes to 0. This is ln of 1, which is 0. So this now has the form infinity times 0. Instead of having this complicated indeterminate form, we have now brought it to a simpler indeterminate form, an indeterminate form that you know how to handle. Right? You know what you're going to do. Exactly, right? The answer we get will be ln of the answer we want. But again, let's just concentrate on finding this answer first. Infinity times 0, exactly, Matthew, right? The usual trick. We will rewrite x as 1 over x. Very nice trick. And now, convince yourselves that you have 0 over 0. So we can apply L'Hopital's rule. Derivative of the top, derivative of ln is 1 over times the derivative of the inside. Derivative of the denominator is this. These cancel out nicely. As x goes to infinity, 1 over x goes to 0. The whole thing goes to 1. So how do we unchange the question now that we have our answer? This is ln of our answer. To cancel the ln, we take the, anybody? What is the inverse of ln? Is the exponential. E to the 1. Right? Because you know that e to the ln x is x. Exponentials and logarithms are inverse functions of each other. We took the limit of the ln, we raise everything to the exponential so that it cancels out. Right? This is the, we wanted x, we found ln x, take the exponential to get your x back. These three indeterminate forms are treated in exactly the same way. Start by taking a ln first. I took the exponential of our answer to compensate for having taken a ln to begin with. And Seelan is asking the good question. Can you take the limit into the ln? So limit of ln, let's say f of x. Is this equal to ln of the limit of f of x? And Shamir came up with the beautiful answer. Yes, because ln is a continuous function. So you see the power of continuity. It's continuity that allows you to interchange the limit and the ln. Very nicely done. Let's take some examples from the book. Does this trick have a name? I don't know that it does. I just called it taking the lawn to begin with. Let's look at what we have here. As x goes to 0, tangent of 0 is 0. So this has the form 0 to the 0. You know what to do. It's one of those 3 indeterminate forms. We're going to start by taking the lawn. This allows us to bring the power down. As x goes to 0 from the right, tan x goes to 0 from values larger than x, right? And that's important so that the lawn itself is defined. You know that lawn is defined on 0 to infinity. So this needs to be positive, which is guaranteed by taking the limit as x goes to 0 from the right. So this goes to 0. And what happens to lawn in that case? You know the graph of lawn. What is happening to lawn? This is changing the question, absolutely. So these two things are not equal. Absolutely. As Shamir points out, lawn goes to negative infinity. So if it wasn't from the right, it would be undefined. Absolutely. The limit itself wouldn't exist because the limit from the left would not exist. So Elizabeth is asking if you can start by taking a lawn. Absolutely. Absolutely. I mean, the answer you get here isn't going to be the answer to the original goal, right? We're going to have to compensate in the end. Everybody comfortable with the fact that we have a 0 times infinity here? And you know what to do. We're going to manipulate this in order to use L'Hopital's rule. I think the typical trick works here, right? X is the same as 1 over x. Can you go over it? I'm not sure what you mean by going over it. Going over what? If we do this, this goes to 0. Ln of 0 is infinity over infinity. This has the form infinity over infinity. When ln approaches 0, it goes to negative infinity. That's correct, Michael? the 0 multiplied by minus infinity. Well, I think Michael has answered the question to that, right? I mean, this goes to 0. Tangent of 0 is 0. So really the question is, what is ln of 0? Look at the graph of ln. I've graphed it before already. Right, as x goes to 0, the ln function goes to negative infinity. All right, so now you have an infinity over infinity. We can apply L'Hopital's rule. Derivative of the top. Derivative of ln is 1 over times the derivative of the inside. Inside is a tangent, whose derivative is secant squared, times the derivative of the inside. Inside is 2x, whose derivative is 2. Derivative of 1 over x is negative 1 over x squared. All right. Since I'm dividing by a fraction, let me rewrite this in the following way. Negative. I'll include the x squared with the tangent. And then we have 2 secant squared. As x goes to 0, secant squared of 2x goes to secant squared of 0, and secant of 0 is 1. So this is not an issue. This thing is not an issue. This, however, let's look at that. This, however, has the form 0 over 0. So we're going to do this part separately. And we're already in a L'Hopital's rule setting here. So we can go right ahead with L'Hopital's rule. The derivative of the top is 2x. The derivative of the bottom is secant squared of 2x times 2. And as x goes to 0, secant of 0 is 1. So the denominator is 2. So you're not in a L'Hopital's rule setting anymore. Numerator is 0, so the whole thing is 0. What are we saying? This limit goes to 0. This limit goes to 1. So you get minus 0 times 2 times 1, which is 0. This limit is 0. But that's not the limit we wanted. It's ln of the limit we wanted. So we're going to compensate by raising everything to the exponential. This limit is 1. How are we doing here? Do we want to do one more, or have we had enough? Questions? Anyone? Is anybody still here? I don't know, it's not hard. Nothing hard here. Let's do one more. Jacob, you can ask me your question after this one. Are you talking, how did I get from step 1 to step 2 on the other problem? Are you referring to the fact that all I did was take the ln? All I did was take the ln, right? Because again, the first thing to do when you've got a limit, no, the one on the other board, sorry. From here to there, I'm dividing by a fraction, so I'm going to multiply by the reciprocal. That's all I did. So instead of dividing by -1 over x squared, I'm going to multiply by -x squared. -x squared. But we don't have times 2. I mean, the 2's still there, if that's what you mean. How did the second half of the equation respond? Well, the secant goes to 1, so you still have a 2, but this 0 makes everything go to 0. What are we looking at here? As x goes to 0, cosine of 0 is 1. Here you've got a 1 over 0, which is infinity. So this has the form 1 to the infinity. You have secant squared of x, of 2x, that's right. Yeah, no, that's all I'm saying, right? I'm saying just the secant goes to 1. This still goes to 2, but you have the 0 there. The 0 makes everything go to 0. No, you don't have secant squared over 2x, over x squared. I'm not sure why you would have over x squared there. When you say 2 times 3 times 4, right, you know what that is. That's 24. That's not 2 times 3 and 2 times 4. No. You don't divide all, right? 2 times 3 times 4 is 24. It's not 6 times 8. That's a mistake you're making. Well, if everything is multiplied together, right? When you multiply 2 times 3 times 4, you don't multiply every term by 2. You just multiply one term by 2. This has the form 1 to the infinity. I assume everybody's convinced themselves of that. So we're going to do exactly the same trick. Start by taking a line, which allows you to bring the power down. And this has the form infinity times cosine of 0 is 1, ln of 1 is 0. This is infinity times 0, but the obvious thing to do, you've already got a fraction here. So we'll do the obvious. As Michael suggests, the limit is e to the 0, which is equal to 1. That's why we had a 1 as our final answer. And as x goes to 0, cosine of 0 is 1, ln of 1 is 0, so you have a 0 over 0 here. So we can apply L'Hopital's rule. derivative of ln is 1 over times the derivative of the inside over 2x. Or if you prefer, negative sine over, whatever. Do we want to say that? Why don't we say negative tangent over 2x? And as x goes to 0, this still has the form 0 over 0. So we can differentiate the top. Derivative of tangent is secant squared. Derivative of 2x is 2. As x goes to 0, secant of 0 is 1. So this is negative 1/2. So we go back and we compensate for having taken the ln. This limit is e to the negative 1/2. Or as Michael suggests, 1 over root e. Very nice. How are we doing here? Questions? Which part of the textbook? I don't know, I'm doing page 316. The part of the textbook known as L'Hopital. Would we have to address restrictions or domain for these questions? I mean, usually the book is pretty good in the sense that no mistake arises. But it's this idea of domain, or do these limits make sense, that should always be in the back of your mind, right? And it's possible that an error has occurred. So you should be quick to point that out if a question doesn't make sense, right? I mean, in the case of, before we had sine, right? And as sine goes to 0, you know sine can take on both positive and negative values near 0, and this would have been an issue. So if this had been sine instead, then here you'd be taking roots of negative numbers, and that would have been a problem. So while I don't think the question will be asking you about domain or anything in here, you should convince yourself that there's no issue with the actual question. I think Jacob had a question unrelated to this, perhaps? Midterm marks, yeah, the marking is crazy. Very time consuming. Hopefully next week. Sealing this exact, well, yes. I mean, I wanted us to prove it. Somebody had asked, it might have been you. I think it was Jennifer. Why? And remind me on Monday, as class starts, we'll prove it. You know, I'm usually here a bit early. We can prove it then. Jacob, you're referring to questions in the book where they ask you to find maybe the 100th derivative or something, seeing a pattern arising. I'm not going to be asking any questions of that form. So in those cases, you're always looking for some sort of pattern that's right in these types of questions. The lecture is done. Yes. If you have questions, don't stick around. I'll just answer a few questions that are coming up here. Somebody wanted me to explain the sine business again. Right, I'm saying here this limit would not make sense if it was sine instead of cosine, because x can take on negative numbers. So sine would take on negative numbers, and then you'd be looking at roots of negative numbers. So that would be an issue. How are we doing? Well, thank you all for coming then. You guys have a good weekend, and I will see you next week. You guys have a good one.